Okay, welcome everyone to the 101st meeting of New Directions in Group Theory and Triangulated Categories. This will be our last meeting before we take a break for the summer. And today our speaker is Janina Letz from Bielefeld and UCLA. And the title of a talk is Generation Time for Biexact Functors and Koszul Objects in Triangulated Categories.
Thank you. Thank you for letting me speak. It's actually funny that you're saying it's the last talk before the summer break for the summer. It already feels like the summer's almost over. I feel like there's not a lot of time left to do all the work you plan to do in the summer. But yeah, I'm also traveling the next couple of weeks, so that might be part of that feeling. So please interrupt me if you have questions, if I make mistakes. I see some of you, others I have no idea, so it would be great or to slow me down, to tell me I'm saying trivial things. Yeah, just feel free to say something if you have something to say. As Retracts said earlier, I gave a talk in the seminar a little bit more than 3 years ago, I think. And I think back then I did like generation and triangulated categories. So it's kind of in the same vein a little bit. But so for those who haven't heard it, I will definitely repeat the definitions that I'm going to use here. So so everything I'm going to talk about is joint work with Marc Stephan, and you can find the preprint on the archive. If you're interested, you can read in parallel, whatnot. So looking at the title, what do I mean by generation time? I always use something. Generation time doesn't really have a fixed meaning for me, I guess. It's just like an idea of a concept. So let me make it precise what I actually mean in the setting of a triangulated category. So let T be a triangulated category with suspension sigma. Then if starting with some object X, we can kind of construct other objects step by step. So in a zero step, we haven't done anything. So denoted by thick 0, that's just the category that contains 0, and I guess all the other objects that are isomorphic to 0. Then in the next step, we want definitely to allow X, and then we want to kind of close it under some type of properties. So this is the smallest subcategory. That is closed under suspension, desuspension, finite direct sums, and direct summons. That contains X. Maybe the most obvious property missing here is the 2 out of 3 property. I mean, I'm calling this whole thing thick. So for thick, if you think about the smallest thick subcategory, usually want the 2 out of 3 property, direct summons, and I guess suspensions and desuspensions. So now this is not closed under 2 or 3. So now from now on, every step we're kind of adding cones. So next step is inductive. So thick n of X. So I'm just writing down the objects. All my 4 subcategories are full, so let's not worry about everything else. So I want to have all the Y's in here that can be built. And by build, I mean they exist in exact triangles. I mentioned it's kind of a cone. Like we want to close it under certain cones. So we have an exact triangle. Y prime to Y direct sum Y tilde to Y double prime. So basically Y doesn't need to be a cone, Y just needs to be a summand of a cone. And then y prime should be in thick 1. And y double prime should be in thick n-1. So this construction goes back to Bondar-Vandenberg. And it behaves actually very well. So here I told you, y prime should be in thick 1, y double prime should be in thick n-1. This is actually like the order doesn't matter. I could have switched the condition for y prime and y double prime, or more generally, y prime should just be in thick I, y double prime in thick J, when I plus J is equal to n. So basically you can choose a decomposition however you want, whatever also in the situation might work the best. Yeah, and in some contexts, so maybe you've seen this before, this is oftentimes also denoted by angle brackets. And I feel like that notation can mean a lot of things, so thick seems to me a bit clearer. Also, like this gives us an exhaustive filtration of the thick subcategory containing X. So in other words, we can define an invariant asking at which point an object is in one of these subcategories, the smallest one when it starts being in here. So that's called the level. So the level of y with respect to x is the first instance such that y is in thick N. And this is the invariant that I loosely mean when I'm saying the title generation time. Sometimes one can also, instead of saying this is generation, one can also say we're building an object out of the other one. But yeah, so those words are not like something precise. I feel like level is probably the precise part. And maybe to give some credit. So this invariant was defined by Abramov, Buchweiz, Iyengar, and Miller. Okay, so maybe I don't know how comfortable you are with these types of things. If you've seen this before, you're probably good. But I do want to give, since I want to use it later on, some way you should think about this. So what all this construction means, and there are a couple of properties go in. So this is not a directly obvious, but it is still a fact. So the level being bounded above by n means that we have a sequence of n triangles. That explicitly tell us how we build this thing. So the first building object is kind of, wait, what am I? Right, yeah, okay. Y1. And then we kind of have these continue until yn-1, yn. Oh, and I'm now seeing that I actually turned them around compared to how I defined it upstairs. But as I mentioned, it doesn't really matter. So here we want all the x's to actually lie in thick 1. And the last y, so the yn, should be y plus y total. So in this whole construction, we only need to be able to take a direct sum and add one step. But yeah, I guess I turned the triangles around compared to how I defined it here. Now the first one is the thick n-1, and the other one is thick 1, and then we get the middle one in thick n. Okay, so I gave you this invariant. The obvious question is why should you care? Why shouldn't you just leave now? Because I should tell you why it's interesting. So so maybe as a first motivation is that it is connected to various algebraic, like various classical invariants. Yeah. So in the derived category of the commutative Noetherian rings, if we take a module, which we view as a complex concentrated in degree 0, then the level of M with respect to R, so we want R to be the thing that's building M, then this is actually exactly the projective dimension of M plus 1. So the way to see this is if you write down your projective resolution, then each projective module is in thick 1 of R. It's a direct summand of a direct sum of the ring. So all you're basically doing, you're gluing these projective modules together to get like your projective resolution. That's the argument for the upper bound. The lower bound is a bit more involved. Just believe me, you get this. So one thing now we can do with level is we could use level to define projective dimension for complexes. There are various definitions for this, and level reflects just different types of properties. It very well reflects these triangulated properties. Or we can do things that like, I don't know, relationships, results for projective dimension. We could try to generalize them maybe to level. So we can use classical techniques, or we could try maybe. And the second part, maybe a second motivation for those who are not coming from, I guess, representation theory or commutative algebra, level is connected to Roquier dimension. In kind of an obvious way. So the thing one can do if one has a strong generator, so we can now also call it generation time, which is not quite true. But if we ask how long it takes, what's like the maximal level with respect to x that exists. So I should put a sorry. So we can find the upper bound. So how long do we maximal, how many steps do we need at most? There is this correction factor -1. Oh yeah, so yeah, should not be. Yeah. Rotratum's question was whether the commutative hypothesis in part 1 is necessary, and actually it is not. This is for any non-commutative ring as well. Yeah. I'm actually, yeah, you don't need commutative. And then the Roquier dimension is the infimo of all these generation times, where for every classical for every strong generator, which just means thick of x equal to t. And the Roquier dimension especially is important. Like, I think people often want to know whether the Roquier dimension is finite, because there are, like, for example, Brown representability theorems. There are lots of things basically saying just look at your generator. If you know things hold for that, you can oftentimes extend it to all of sig of x or sig n of x. So if you know bouquet dimension is finite, you just oftentimes have to work with one object. So that's why bouquet dimension is interesting. Okay, maybe I'll pause here. Any questions about like level, sig, any questions that haven't been already asked in the chat? Okay, then let me continue. I want to mention two facts about level. That will that we'll use later on some level. So if we have an exact functor between triangulated categories, and we take two objects in S, and compare, and we want to see what happens to level when we apply F. So when there are two categories involved, I put the category which I'm working in the index. Then here the f of x and f of y. So basically we said if for the x level of y, we have like the sequence of triangles. We can just apply f to that, and we already get like, and those triangles also build f of y from f of x. But maybe there's a better way of doing it. So in general, we have the inequality. And then the second thing, for transitivity, so if you build y out of x and z out of y, what do the steps tell us about how fast we can build z out of x? And this actually has a very bad inequality. So if we kind of want to go the whole way compared to just going part way, and this has a product thing. So the upper bound is a product of the other two, and products are pretty bad in general. But in this generality, there's actually no way of doing it much better. Yeah, but what I want to talk about now, or it's already, is to get into a situation where we can do better, where we can get away from this product and get a much better upper bound. And that's where biexact functors come in. So why biexact functors? I mean, I'm telling you there are these good or bad inequalities and we can improve them, but why do I want to talk about biexact functors?
Sorry, Janina, can you please go back up? I haven't copied everything. Sure. Thanks.
Yeah, let me know when I can continue. I guess I can also, yeah.
No, I'm done. Thanks.
Okay, perfect. Yeah, please slow me down if I'm too fast. I have a theory how I space things on this thing, because at some point I have diagrams already written. So that's why I was moving this quickly down, because I guess I'm writing a bit tighter together than in the notes that I prepared. Okay, why biexact functors? So honestly, the main example, or the example why we started thinking about this, was the tensor product. So I mean, there are definitely other ones, but at the end of the day, the tensor product was the motivation, and I feel like it is also the main biexact functor people oftentimes consider. I guess of a TT category. So in particular, the question is, what can we say about the level of y tensor y prime And I'm gonna leave the generator open for now. You'll see in a moment why. So we kind of want to basically bound the level of y tensor y prime by the level of y and the level of y prime. So classically, a couple of things are known. So for modules, and I guess here let's say commutative here, because otherwise the tensor product, you would need to do left and right modules, which I'm too lazy to do. But yeah, if you're interested in that, you can probably translate it yourself or ask me after. So for our modules, it's known that the projective dimension of M tensor R n is bounded by the projective dimension of M plus the projective dimension of N. Sums are better than products. And then this was already just slightly generalized by Aframov, Iyengar, and Niemann. So if we're in the derived category of a commutative ring, and we're taking R as our generator, so we're looking at the level of X tensor Y, then they showed that this is bounded by the level of X plus the level of Y minus 1. So this is a generalization. If I'm kind of fudging a little bit on the tensor product, on the derived tensor product versus the tensor product, because so here note that level is actually projective dimension plus 1. That's where like this minus 1 comes out in the level inequality. So this kind of gives us a motivation, right? What we might want to prove in general. The only thing that we had to figure out first was what to do with the generator. So the thing to observe here, R is the unit of the tensor product. So we actually have R tensor R is the same as R. So yeah. So that's what I meant with putting a question mark up here. Here we want to actually have X tensor X prime and then compare it to the level of Y with respect to X and Y prime with respect to X prime. Okay, so I'm kind of telling you a little bit like how we started this. So the very first naive approach. Let me switch to general biexact functor. So if you're more comfortable, feel free to think about it as a tensor product. I'm just going to write a biexact functor. It has two inputs and satisfies basically the same conditions as a tensor product does. I mean, without the associativity and things like that. You know what I mean. Okay, so given object, 2 objects in S and 2 objects in T, the thing we're interested is we want to start at f of x comma x prime, and we want to get to f of y comma y prime. And we kind of want to have an upper bound to what the level is to go from f of x comma x prime to f of y comma y prime. So the first naive thing one could say is, okay, why not go through one of these? First do the first component, then do the second component. So here this one would be bounded above by a level x of the x level of y. The other one would be bounded by the y level. So this would now bound this level by the product of those two. So this is using the two properties that I told you earlier. F blank comma x prime is just the functor, and then this is a transitivity type of thing. Obviously, this is very bad. But good news, the reason I'm telling you about all of this is that we can do better. So the idea is, instead of kind of going all this way around, we want to go through the middle, right? We want to kind of have a simultaneous type of thing. In other words, this means we need to use both components at the same time. Okay, so now my big diagram is going to come up. So setup. So I'm kind of first telling you the idea of the proof, and at the end you'll get the statement. So, okay, let's assume the level of y with respect to x is n, the level of y prime with respect to x prime is n, which means we have like these sequences of triangles that's building from these x's. We get ym, from the x primes we get yn prime, and then in the sums they decide y and y prime are sums of ym and yn prime. And then we can draw a big diagram. So basically what's happening is I'm only interested in the maps between the y's. So basically for all the maps that I drew in this diagram, the cone will be, yeah, we know the cone. Let's just say it like that. And currently, yeah. And the thing we want to do, we want to get here. This is the thing we want to build. And the question is, how can we do that? And we said we want to go along diagonal. So the idea is, okay, we take this, we take this, and so on, and eventually we'll land here. And which, in other words, we need to construct maps between the diagonals that have a cone that consists of the right building blocks. So in other words, we need to. So when I draw these along the diagonals, what we're doing, we're taking homotopy pushouts. So in some sense, we're taking sums, if you want to think about all of these as submodules of one big thing. But the issue is working in triangulated categories. We don't have pushouts. We can't do this like in a unique enough way. So, so the construction, just to drop some names, some names of some objects. So take we want to take homotopy pushouts, and we want to make sure that then the maps between these homotopy pushouts have the right cone. And then and this is where the usual problem comes in with triangulated categories. So problem, my tablet is dying. No, it's not. Okay, sorry. Yeah, so the usual problem is we can't, like in general, we can't control all the things at once. So we want them to be compatible enough, and we want to control the cone. And in general, that's not possible. The problem in triangulated categories. I mean, I guess they're very like, I guess kind of, okay, categories, I guess morphisms, constructing morphisms is not unique. Let's say it like that. So this means especially think about the axiom of the triangulated category. If you have, when you construct a morphism between two triangles, if you have two morphisms given, a third one exists. But that's very non-unique. And that's also the thing where, say, homotopy pushouts aren't pushouts. So it does behave as a pushout in the sense of there's always a map, but that map is not canonical, it's not unique. So somehow we have to be able to control that morphism to also, in the end, get it to satisfy all the properties we wanted to satisfy. And the usual answer, if we run into these types of problems, is we need an enhancement. Okay, so now I can give you the statement. I actually don't want to talk about the enhancements too much. I basically just want to say we need more structure. If you know about them, you're good. You know what I mean. If not, just think about it. If your favorite triangulated category, derived category, a stable module category, the topologists have their own, which I don't know that much about. But all of them, we construct them in a certain way. For derived category, start with chain. We always know we can lift things back to chain complexes. For a stable category of an exact Frobenius category or something, you can also lift things back. So there's actually much more structure there than the triangulated category sees. So that's what I mean when I say enhancement, that we kind of just remember that information. Okay, so let F be a biexact functor of topological triangulated categories. Then the expected inequality holds. Let's say it like that. And yeah, and topological here stands for it having some extra structure. Yeah. Let me pause here. Are there any questions? I'm saying a few more words about topological triangulated categories in a moment, but I just want to check. Are there any questions?
So does this fail for algebraic triangulated categories?
Sorry, sorry, I didn't hear the whole question, but something about algebraic. So
what happens if you assume that they are algebraic triangulated categories?
Oh, so every algebraic triangulated category is topological.
Oh, okay.
So in particular, this holds for algebraic ones.
Okay.
Yeah. Any other questions? Okay, then let me say at least a little bit. I don't want to get into details, but maybe just say a bunch of words that hopefully give at least a little bit of context. So loosely speaking, all triangulated categories that appear in nature are topological. Which is always, I mean, nature's a thing that we say in math, which is sounds to me oftentimes sounds weird, but I think, yeah. So this is kind of, so usually all the triangulated categories you think about are topological, so we don't have to worry about this. Maybe for precise definition, a topological triangulated category is the homotopy category of a cofibration category. And maybe since Lucas asked about algebraic ones, the algebraic triangulated categories are precisely those where the cofibration category is additive. Or I think it's, or maybe it's a subcategory of that, like one of both, but you have like some additive property to get algebraic. And yeah, a cofibration category, it's kind of very similar to a model category. If you have a model category and you just look at the cofibrant objects, now I feel like I might say something wrong. But basically in the cofibration categories, you only have cofibrations and weak equivalences, and that already gives you enough. So it's a bit more general than a model category, but out of every model category, you do get a cofibration category. So if that's a setting that you prefer to work with, you're good. Everything you do, all the categories you get, triangulated categories you get from that are good. So yeah, so we have cofibrations, there are weak equivalences. And the push outs along cofibrations exist. So in other words, by going to this cofibration category, we can suddenly work with push outs. We can do things in a canonical way. And that's kind of how the proof goes, showing that we can construct these triangles, these homotopy push outs. Upstairs, we can construct them as honest push outs. And then we can do all the things we can do with push outs. Maps are unique. We can say it's easier to compute what the cone is, etc. So suddenly that's solving all the issues. One more thing to mention, the biexact functor up here, I'm saying it's a biexact functor of topological triangulated categories. What I mean by that is that we can also lift it to a cofibration category. So a biexact functor of topological triangulated categories is a functor induced by a biexact functor upstairs. And the biexact just makes sure, so the exact makes sure that it's kind of compatible with the structure of the cofibration category. The bi makes sure that the two components of the functor are compatible with each other in a reasonable way. Okay, so I said all categories you care about are usually topological. So let me give you maybe the main examples one might be interested in to apply this to. I say many tensor triangulated categories. I think, yeah. So the most common one, the ones people study are all fall into this setting, also in a setting where the tensor product comes from the cofibration category. So maybe to be more explicit, we take the derived category of modules over a commutative ring, the tensor product over R, and R is the unit for a commutative ring. Here, commutative is important, otherwise the tensor product would not be a tensor product. Like, it wouldn't be well defined. Then there's also the stable module category of a group algebra, tensor product over K, and K is the unit. There are also some topological triangulated categories. What I mean by that is triangulated categories coming from topology, which I don't know much about. So let me just, yeah. So for example, the homotopy category of equivariant spectra. But basically every tensor triangulated category that's induced by a symmetric monoidal stable model category. And that's a lot of them. Okay, I'll pause again. Any questions?
So does the level have an intrinsic meaning in the last two examples?
Oh, so you mean similar to how it's connected to projective dimension?
Right.
I don't know. I think it depends on the generator a lot, right? So I actually haven't seen any. So all the examples that I've looked at were the derived category. But again, to be fair, that's also the category that I'm mainly interested in. So yeah, the answer is I don't know.
Okay, thank you.
So sorry if it's obvious, but I guess derived categories of Hopf algebras also fall under this list of examples.
So derived categories fall into this example. Yes.
Derived categories of a Hopf algebra.
Sure. All derived categories of any exact category.
Okay.
Fall into this example. I mean,
Thanks.
If it okay, so without the tensor product for now, but yeah. Okay, there's a question in chat. Is there any interpretation for the stable homotopy category? I feel like this is a topological question where I'm just uncomfortable with, that I don't know anything about. I don't know whether Marc knows something about this. Okay. Yeah, sorry, I don't know.
So the stable homotopy category is one of the examples. If you just take a trivial group, then you can look at it as equivariant spectra. But I mean, this is also one example. Yeah.
Okay, thank you, Marc. So yes, it is a topological triangulated category. Okay, so wait, how much time do I have until, is it 50 or 60 minutes? They have 5 minutes or
60.
10 minutes?
60 minutes.
60 minutes, okay, 15 minutes, okay, then I'm good. So, okay, so I'm working through my title, right? So I'm done with generation time, I'm done with biexact functors, so let me talk about Koszul objects. First, what is a Koszul object? Right. Let me, sorry. Just need to look. Here we go. Okay, so for every triangulated category, we have a graded center. So we have a ring that's naturally acting on it, and it's kind of the biggest possible ring. So the graded center of a triangulated category T is defined to be.
So Janina, I think it's not anymore updating.
Oh, okay.
Or I can. Yeah.
Yeah, no, I saw the same. I have it on my
Okay.
laptop, and I do agree with you. Let me just share it again. Hopefully it'll be fine. Maybe I'm just testing whether everyone is awake. Okay, it's at least updated a little bit now. Let's see whether it'll continue. If not, I'll have to go back and forth for a while. Yeah, okay, it seems to be fine. Yeah, so the graded center is, okay, technically we don't know whether it's a set, but let's ignore those issues. So it's a graded set, and the elements are natural transformations from the identity functor to the Dieth suspension, such that it's compatible with the suspension. And if this is actually a set, this is a graded commutative ring. So now the Koszul object so if we take the Koszul object of C elements in the center, on some object is so this construction generalizes the Koszul complex. So in other words, if we have no elements at all, we just have X. To construct a Koszul object, what we actually do, we just take our module, we take multiplication by M, and we take the cone of that, right? That's then a complex where M is constraining degree 0 and 1 with multiplication by X. So we do the same here, take the cone of X to, I guess I have to do some type of suspension of X. So we take the cone of this, this equal to 1. And then for all higher, if you have more elements, we just do an inductive step. So this is called a Koszul object, and it is denoted by X, 2 lines, alpha 1 to alpha C, which are already used in C bigger or equal to 2. I'm not saying, but yeah. So this generalizes the Koszul complex. So if you just do it in like derived category, you get exactly the Koszul complex back. Yeah. But maybe some warnings. This construction is not commutative in the sense if you take the Koszul object of alpha and beta, that's not the same as the Koszul object on beta and alpha. So like it behaves pretty badly because usual problem, the cone is not functorial, maps we construct are very non-unique. So all of this, while the Koszul object is unique up to isomorphism, it's only unique up to non-canonical isomorphisms. So it doesn't always behave very well. Yeah, so this is the Koszul object. And I'm talking about generation time. So let's look at the level. Naively, if we start at X and we want to build a Koszul object on X, we have this inductive construction. And just by the construction, this is bounded by 2 to the C. Basically, so already for 2 element, it's basically you do something from thick 2 and thick 2, so you get something thick 4 and so on. So this is a pretty bad bound. Especially if you think about the Koszul complex, where we know the projective dimension is at most C plus 1, or C, I guess. So this is very bad. As I mentioned, because the Koszul object doesn't always behave particularly nice, So because of that, I want to restrict ourselves to very specific elements in the center and elements that come from action of a triangulated category. So if we have a monoidal triangulated category S acting on T, so for in this situation, so an action on T just means it's kind of compatible in the right way with the monoidal structure. So some type of associativity, some type of unital conditions. If we have such an action, then we get a ring homomorphism from the endomorphisms of the unit of S to the center of T. In other words, suddenly, so every action gives us elements in the center, so we can take Koszul objects with respect to elements in the endomorphism ring. So, and these behave much, much better. So we can choose these to be functorial in a reasonable way. So if F is an endomorphism, then the Koszul object, we can just choose it to be F of the cone of F by X. So by this choice, this is functorial in X. So now things behave much nicer. Yeah. Maybe I should just say property. And then in this situation, we can give a better bound on the Koszul object. So theorem. So if we have basically for every element alpha 1 to alpha c, we want to look at a different, we can look at a different action. So let's say we have actions fi, be actions of topological triangulated categories, of topological tensor triangulated categories. Si on tensor on the topological triangulated categories. And we take, for every I, we take an element fi in the endomorphism ring of Si. Then the level of the Koszul object with respect to X is bounded above by C+1. And this is a much more satisfying bound, and it is actually sharp in many situations. So this, we can't do any better. Okay, so to the end, let me mention two more examples for this. Two examples for this. One is the obvious one, I guess. The tensor triangulated categories. Another example from a commutative algebra perspective, that's something one would look at. Let's say R is a commutative ring. S is an associative R algebra. And we look at the derived enveloping algebra. S tensor over R of S. Then one has the monoidal triangulated category that's the derived category of the enveloping algebra, has a tensor product over S, unit S. This thing acts on the derived category of S. And the endomorphism ring that shows up here S, S is precisely the Hochschild cohomology of S over R. So in other words, the above inequality holds if we use if it's elements, if we take the Koszul object with respect to elements in Hochschild cohomology. But yeah, there are different actions as well. But yeah, most rings people look at that act on a kind of naturally on the triangulated category come from such settings. Okay, I'll stop here. Thank you all for following.
Thank you, Janina. Let's all give the speaker a round of applause.
Doesn't work that well online.
Sorry?
Applauding doesn't work online.
Yeah, because some people applaud the more online savvy way.
Yeah.
With the yellow hands.
I saw
okay.
that, so you're good.
Okay, any questions for the speaker?
So you mentioned in some sense these Koszul objects recover the Koszul complex. So is there any relation of these to Koszul duality?
I don't know. No. I wouldn't expect it, let's say it like that, but actually, no, I haven't thought about it. Have never thought about it.
Okay.
Thank you, Lucas.
I have a question. So are there general methods of getting lower bounds for the level? For instance, for the projective dimensions, like one can look at X groups, and if that doesn't vanish, we would say we can't get shorter than that. How do you get lower bounds in this business?
Okay, so lower bounds you get through ghost maps, or so-called ghost maps. There's a theory, so that's also the way how you show that level is actually equal to the projective dimension, not just less than or equal to. In general, it can be much harder to get the lower bounds. So the way you do it, basically you approximate. They're like, I don't know whether do you know about approximations? So the maps where every other map factor is through. So basically you want to, yeah, so there is a construction which is actually very similar on how you construct projective resolution by taking like a surjective map onto the kernel and continuing that. So there is a more general way of doing that. The issue with that is it's not always known to work. So in the settings where we often look at level, that's like small categories where we don't have arbitrary coproducts. We can't do those, we don't know whether these constructions always work. For that, you need a big category, but then suddenly looking at level is weird. So there is a little bit, there's a lot of open questions there, which I find very interesting. Yeah.
Thanks.
Thank you. Any more questions or comments?
This way I can see more people.
Right. Yeah, I don't see any other questions. Okay, in that case, let's thank Janina once again. Okay, thank you all for coming. We will be back hopefully in October. Bye-bye.
See you.